In Chapter 9, we're going to come back to making inferences for categorical data, and we're going to talk about a new distribution called the chi-square distribution. And there are 3 different types of tests you can run with the chi-square distribution, and each section is going to cover a different test. And in Section 1, we are going to start with the chi-square goodness of fit test. So remember, in Chapter 6, we talked about proportions, and we discussed inference procedures for comparing the proportion of successes for 2 populations or treatments. And the chi-square tests allow us to take it further. So the first test allows us to examine the distribution of a single categorical variable in a population. And this is called the chi-square goodness of fit test, which allows us to determine whether a hypothesized distribution for a single categorical variable is valid. And it answers the question, do the data fit well compared to a specified distribution? So this is what we're going to cover in this section of notes. In Section 2, we want to decide whether the distribution of a categorical variable differs for 2 or more populations or treatments. And this is called the chi-square test of homogeneity, which allows us to determine whether the distribution for several categorical variables across 2 or more populations is valid, and helps answer the question, do 2 or more populations have the same distribution for one categorical variable? And in our last section, we are going to study the relationship between 2 categorical variables across a single distribution. And this is going to be done using something called the chi-square test of association / independence, which allows us to determine if there is convincing evidence of an association between the variables in the population at large. And it answers the question, are 2 factors or variables independent for a population under study? So to start off, we're going to talk about the hypotheses for a chi-square goodness of fit test. And the null hypothesis is going to state a claim about the distribution of a single categorical variable in the population of interest. So our null hypothesis is going to say all proportions are as stated. And then what we do is we state our proportions. So our p sub i's, however many proportions we have, are equal to their purported value. The alternative hypothesis is that the categorical variable does not have the specified distribution. So our alternative hypothesis is going to be at least one p sub I is different than stated. And there's really no mathematical way to write this. It's always going to be that same sentence for every alternative hypothesis. So when we are running a chi-square goodness of fit test, we compare observed counts from our sample with counts that would be expected if the null hypothesis is true. And the more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis, which means the difference between them was so large we can no longer say that it was due to sampling variability. And the way we are going to get our expected counts is by multiplying the proportion of the population distribution in each category by our sample size. So to see if our data give convincing evidence against the null hypothesis, we compare our observed counts from our sample with the expected counts, assuming our null hypothesis is true. And if the observed counts are far from the expected counts, that is the evidence we were seeking. So when it comes to our chi-squared statistic, it is the measure of how far the observed counts are from the expected counts. And chi is a Greek letter. It is the fancy X you may see. So we say chi-squared, our statistic, equals the sum of our observed minus our expected squared over our expected. So you want to think of chi-squared as a measure of the distance of the observed counts from the expected counts. So larger values of chi-squared are stronger evidence against the null because the observed counts are far from what we would expect if it were true. And then smaller values of chi-squared suggest that the data are consistent with the null hypothesis. When it comes to the sampling distribution of a chi-square statistic, it is not actually a normal distribution. It is right skewed, and it only allows for positive values because the statistic cannot be negative. Because we're talking about distance, distance cannot be negative. And our degrees of freedom actually change the shape of our chi-square distribution. So different degrees of freedom give you a different distribution for your graph. And when the expected counts are all at least 5, the sampling distribution of your chi-squared statistic is close to a chi-square distribution with the degrees of freedom equal to the number of categories minus 1. So your degrees of freedom is n minus 1, where n is your number of categories. So when we talk about the chi-square distributions, they are a family of distributions that take only positive values and are skewed to the right, and a particular chi-square distribution is specified by given its degrees of freedom. And the chi-square goodness of fit test uses the chi-square distribution with degrees of freedom equals your number of categories minus 1. And so here's kind of an example of a chi-square distribution with degrees of freedom 6. Which you can then use to calculate your p-value. And the p-value is the probability you get that chi-square distribution or more extreme if H naught is true. It's basically saying what is the probability that this difference is due to chance variation. And then you can compare your p-value to your level of significance and determine if you have enough evidence to reject or fail to reject. So when it comes to our conditions for our chi-square goodness of fit test, we don't really check them because some of these we just kind of assume are already met. So for random, the data came from a well-designed random sample or randomized experiment. For our independence, the 10% condition is met, and we don't really check normal because it's not a normal distribution. We check just to make sure we have a large enough sample size, and we hope that all expected counts are at least 5. And that allows us to say that the sampling distribution will follow a chi-square. So again, we don't really have to check the conditions. They're usually just all met in general. So we assume the random, independent, and large counts conditions are met, and then we determine whether a categorical variable has a specified distribution writing our null hypothesis and alternative. Again, we're going to specifically write them using P sub I. We're not really going to write them in words. We're going to follow the second one. So our null hypothesis is going to be P1 equals, P2 equals, P3 equals, so on and so forth. And our alternative hypothesis is going to be at least one of the PIs is incorrect. So we start by finding the expected count for each category, assuming our null hypothesis is true, using the statistic that we have already stated. And then we have that our p-value is the area to the right of chi-squared under our density curve of the chi-squared distribution. With this is k minus 1, where we use n minus 1 degrees of freedom. So n is our number of categories. So couple of things to keep in mind. Chi-squared test statistic compares observed and expected counts. So we don't try to perform calculations with our proportions. We only use our numbers. And we don't really check the large counts conditions because, again, all of our data is going to be pretty much large enough. Right, so in our example, we have that a geneticist is studying the gene pattern of eye color in a group of white mice. He observed a random sample of mice from the lab and found that 119 had red eyes, 48 had brown eyes, 32 had pink eyes, and 13 had blue eyes. His model suggests that this distribution of eye color should occur in a 9:3 to 3:1 ratio. Is there evidence that the geneticist's model is not accurate? Use a 5% level of significance. So our null hypothesis is going to be that our proportion is equal to what's stated. So to convert a ratio to proportion, you add your numbers together. So 9 plus 3 plus 3 plus 1 is 16. So all of those numbers get put over 16. So that tells me my proportion of red eyes is going to be 9 over 16, which is 0.5625. My proportion of brown is going to be 3 over 16, which is 0.1875, which is also the same as my proportion of pink. It's also 3 over 16. And then the proportion of blue is going to be 1 over 16, which is 0.0625. And then our alternative hypothesis is that at least one P sub I is different. So those are our null and alternative hypotheses. Now we need to go ahead and do our expected and our observed. So I'm going to go ahead and create a table just because it's easier to look at. So we have our observed and our expected. So our observed come directly from what's stated. So we have red is 119, brown is 48, pink is 32, and then we have blue, which is 13. Now to find my expected, I find my total sample size, so 119 plus 48 plus 32 plus 13, so 212. And now I'm going to multiply that by each of my proportions from my null hypothesis. So we're going to do 212 times 0.5625, and we're going to get 119.25. 212 times 0.1875 is 39.75, so that's the same for brown and pink. And then for blue, we do 212 times 0.0625, which is 13.25. Your expected values do not have to be whole numbers. They can be decimals. So now we'll go ahead and calculate our statistic. So our chi-squared, we're going to do 119 minus 119.25 squared over 118.25 plus 48 minus 39.75 squared over 39.75 plus 32 minus 39.75 squared over 39.75. And then our last one, 13 minus 13.25 squared over 13.25. We do want to try to put that in our calculator all in one step. And we're going to get that our test statistic is 3.229. Now to calculate our p-value, we are going to go to second vars, and you're going to go to second vars, and then you want to go to 8, which is our chi-square CDF. So you'll do lower and upper bound just like we've done before. So our lower bound is going to be 3.229. Our upper bound is going to be 1E99. And then for our degrees of freedom, we take our number of categories 4 and subtract 1, which is 3. And we are going to get a p-value of 0.3576, which we are now going to compare to our alpha, which is greater than 0.05. So in this case, so we are going to fail to reject our null hypothesis, which means we do not have enough evidence to show the geneticist model is incorrect. The last thing I'm going to talk about is how you can do a chi-square goodness of fit test on your calculator. So just like we could run a significance test for proportion on a calculator, you can do the same thing for a chi-square. So the first thing you have to do is enter your observed counts into list 1 and your expected counts into list 2. Then you're going to go to stat and then tests, and then you want letter D, which is your chi-square goodness of fit test. So your observed list should automatically be list 1, your expected list 2, and then you'll input your degrees of freedom, which in this case is 3, and then you would hit calculate. So it will give you your chi-squared statistic, which matches what we got, and your p-value, which is a little bit more accurate. It's 0.3577, and then it gives you your individual contributions to the chi-square statistic. That's what CNTRB is. You can ignore that. We're not going to be using it. So all we care about is the p-value from this screen, which you can then compare to your alpha. So again, not going to be different enough that it should change our conclusion, but it might be slightly more accurate because we didn't have to round our statistic. So let me know if you have any questions about chi-square distributions or performing a goodness of fit test.